Well, good morning, students. It is Wednesday, April 15th, 2020. It's time for some earth science. So, today we're going to talk about faults. No, I don't mean things like procrastination and laziness and stuff like that. I'm talking about faults in the earth, those cracks. Okay? We're going to have three types of faults that I want you to know about. You should be able to name them and describe them, what's going on. And with them, you can identify what types of stress are involved and what type of plate boundary is associated with those faults. First, let's do a little review. Monday's video. I get confused because I'm actually recording this on Tuesday. So, Monday's video, we talked about some basic vocabulary and features dealing with earthquakes. And you had this diagram which you were supposed to go into a Google form and answer some things. And by the way, what I looked at, quite a few of you gave good, reasonable answers for that. A couple of you had incorrect answers, all right. And a couple of you had answers that were ridiculous. I'm sorry, but when I say what feature or phenomena is being indicated by letter A, and you tell me letter B, I don't think you took the question very seriously. And you're not helping yourself when you do that. Excuse me, got a little tickle. So anyway, here's our surface of the earth. And here's this crack going down into the earth. And A is pointing to that crack. So, in your answers, A should have been a fault. Now, technically, a fault, we need more than just a crack in the earth, because that could be a fracture. There has to be movement, some sort of movement along that crack for it to be called a fault. E indicates that there was some movement that happened. Okay, that's what I was trying to say. Some sort of energy disturbance is happening there. And that point at which the motion takes place is called the focus. D is the point directly above the focus on the surface of the earth. So if you were on the surface of the earth, that is the closest point you can be to where the earthquake actually happened. D is called the epicenter. Epicenter is what you always hear about in the news reports when they talk about an earthquake happening. They say the epicenter was located 6.3 miles from such and such place. Okay? What are some other things here? B is referring to the angle between the horizontal surface and that crack in the ground. And that angle has a really fun scientific name for it. It's called a dip, or the dip. And so that leaves us with C and F. And C and F are referring to just this big mass of earth and rock here and here. And when you have this fault dividing it, you say this mass is on the bottom and this mass is on the top. Okay? And I said yesterday, or Monday, that if you imagine yourself in a tunnel that's right along that fault, and you're standing in the tunnel, your feet are on this slab of rock. That's called the foot wall. Okay? And then you have your lantern, and you hang your lantern up. Your lantern is hanging from this slab of rock. That's called the hanging wall. Okay? So out of 2, 4, 6 answers, I hope you answered all 6 correctly. I will expect you to be able to do that. You're probably going to have something very similar to that on a quiz, or in some way, shape, or form, you're going to be asked this information again. All right, so let's talk about the types of faults. So, number 1, we're going to start out with something called a strike-slip fault. And we're saying this fault is under shear stress, side-to-side stress. Now remember, shear, here's the scissors, or another word for scissors is a pair of shears. In a shears, the one blade is sliding past the other one. They're not coming directly at each other, they're sliding past each other. That's shear stress. And I need to grab a model for myself. Sorry, be patient with me. I forgot where I put my model. I got it now. Sorry about that delay. So, here's my model, and imagine this is two slabs of rock, and there's this crack between them. So in shear stress, what we're saying is these pieces are moving side to side without much up or down movement. Okay? We have this shearing action. Okay? This type of fault, if the slabs of the earth are moving sideways like this, that is called a strike-slip fault. So, lots of horizontal movement, very little vertical movement. These types of faults are related to transform boundaries. So, in the last chapter, we talked about plate boundaries. So, if I have two huge pieces of continental crust or any crust, and they are sliding sideways relative to each other, that's where we get strike-slip faults. That was called a transform boundary back in that last chapter. The dip, which is the angle between horizontal and our fault, in strike-slip faults, the dip tends to be fairly vertical. And let me compare that for you. In this model, the dip is much more angled. Okay, so strike-slip faults tend to have fairly vertical dip. The San Andreas Fault in California is a major example, one of the most famous examples in the world of a strike-slip fault. Okay, in the San Andreas, you've got the United States, including part of California, and then on the outside of California, the parts of California are actually attached to the Pacific Plate, where most of California is the North American Plate. And what's happening is that Pacific Plate is sliding up alongside the North American Plate there. And so Los Angeles is on the Pacific Plate, San Francisco is on the North American Plate. Los Angeles is sliding relatively north compared to San Francisco. So if it keeps going at that trend and we wait long enough, a long time, Los Angeles is going to be next to San Francisco. Wow. But that's geologic time frames. A couple of pictures here. I don't think they built the road originally this way. Okay? So you see a road, and now you see a road. And the road has gotten moved over based on the size of the picture. I'd say it's moved over about 8 feet, a couple of meters. That looks like evidence of a strike-slip fault. The motion seems to have been sideways, not a lot of vertical. Yeah, there's a little bit of change in elevation there, but not much. Either something geologic happened here, or we've got a farmer who's really doing some strange things in their field. It looks like this field was all seeded, nice, straight rows, and the earth cracked and moved. We had mostly horizontal movement. That looks like evidence of a strike-slip fault. So here we had a fence. You can see the fence going off into the distance. Here the fence is continuing towards us. And I think that fence used to line up. But the two pieces of earth have moved. And you see that there's lots of jumbled debris here where the sod's been tore up and things like that. So the two pieces of earth moved. Either that piece moved that way or this piece moved that way, or they both moved some. We don't really know. But again, it looks like it's moved probably 8-10 feet in that example. Strike slip. All right, next type of fault. It's going to be called a normal fault. Okay? So here we're going to use this example. We got these two slabs, and the fault is in between. The fault is, it's got kind of an angle dip to it. And the hanging wall is going to effectively slide down relative to the footwall. Okay, the hanging wall is always the one that's on top. Now, if you can imagine that I pull these apart from each other, and it's hard to demonstrate that perfectly, but if I pull them apart, gravity pulls down on this. And so the way I think about it is the hanging wall's on top. What's the normal direction for things to go just due to gravity? Well, the normal direction due to gravity is down. And so the hanging wall falls down. So we're saying in this case there's a lot more vertical movement, not so much side-to-side movement. If you see some evidence of this, that's called a normal fault. Now, what causes that? Again, it's under tension stress. Tension is when we're pulling. The last one was shear, this one's tension. They're pulling apart from each other and the hanging wall slips down. And so that's associated with a divergent boundary. Okay? Divergent boundary. So, I'm not sure how well this is showing up with the picture on the video. I hope it is. You can see a big wall of rock that's been exposed. This right here, if you can't make it out, this is a person standing in front of the rock. So this is a big wall here. But you see these color stripes, and you can tell that this darker rock here lines up with this darker rock here. And so at some point in time, they should have been together. So what's been the relative motion? The hanging wall, the part that's above the crack, the hanging wall seems to now be lower than it used to be relative to the footwall. So if the hanging wall has fallen down, that's the normal direction of gravity. Looks like a normal fault. This one I can't tell as much, but I think it fits the example of a normal fault. This guy is, I hear he's outstanding in his field. Sorry. So you see that there's, maybe 2-3 feet where things have shifted. And to me, I think I can picture in this that this slab has dropped relative to this slab. It's a little hard to tell, but that might be an example of a normal fault. Okay. Let's go to our third type. And this is called a reverse fault. So if normal is where the hanging wall drops downward, well, what's the reverse of normal? What if we push these together and you see that all of a sudden the hanging wall moved upward? The hanging wall has shifted upward relative to the footwall. Okay? So normal fault, hanging wall drops down. Reverse, the hanging wall pushes upward. Okay? And how does that happen? They're being squeezed together. If I squeeze these together, the hanging wall moves upward. So, it's under compression stress. It's being squeezed. The hanging wall pushes upward. That's associated with a convergent boundary, the coming together. And the reverse fault, if this dip is less than 45 degrees, is sometimes referred to as a thrust fault. And it's being thrust upwards over the other one. I thought this was about the clearest example that I could find in trying to search around for a reverse fault. this rock face, somewhere along the way, this has all eroded away, and this rock has been exposed. But when you look at the lines in the rock, it seems very clear that this piece of rock matches up with this piece of rock. But the hanging wall, the part on top, has shifted upward. It's been pushed upward, it's been reversed. Okay? Reverse fault. Here's a smaller scale example. There's a hammer over here for comparison of size, but we got this crack, and it looks like this, you can see how the color patterns line up, and it looks like the part on top, the hanging wall, has been pushed upward. This one isn't quite as clear, but to me it looks like the slab on top has pushed upward some. Now, both normal faults and reverse faults are called, oh, this is a fun science word, they're called dip-slip faults. Okay? Remember, dip is the angle between horizontal and the fault, and the slip is the motion of the chunks of rock. And so in both cases, whether it be a normal fault where it's slipping down the face of the fault, or reverse where it's being pushed upwards, it's slipping upwards along, it's slipping along the dip. Dip slip. So, let's just practice a little bit. Your choices are strike slip, normal fault, reverse fault. Think about it. Hope you said strike slip. The motion was sideways. Okay? Your choices are strike slip, normal fault, reverse fault. I hope you said normal fault. The hanging wall has slipped downward relative to the footwall. Choices are strike slip fault, normal fault, reverse fault. I hope you said strike slip. Looks like the motion was side to side. Choices are strike slip fault, normal fault, reverse fault. I hope you said reverse fault. Looks like the hanging wall has been pushed upwards relative to the footwall. Your choices are strike slip fault, normal fault, reverse fault. I hope you said strike slip. Looks like the motion is mostly horizontal, not much vertical. Choices are strike slip fault, normal fault, reverse fault. I hope you went with reverse fault. It looks very clear to me that the hanging wall has moved upwards relative to the footwall. This one's a little harder to judge. Make a guess. I would say this looks to me to be an example of a normal fault where this part has fallen downward. We can't see enough of the angle to really identify the hanging wall and footwall, so I would avoid that for a test question. This one, again, is a little bit harder to tell, but take a guess. To me, it looks like this part has been pushed upward relative to this part. I think that's an example of a reverse fault. And that's as far as I'm going with today's video. We'll have some other work for you to try. Have a great day. Stay safe.